Thanks for inviting me to give this talk. It's really an honor to give a lecture in this series. And I also want to first of all thank you guys, everybody, for sort of tuning in from close and far, and also the staff at Simons for sort of putting together this remote presentation in such a short time. So the talk is titled "Lattices Intersect Quantum," and let's see if I can swap the next slide. Good. And what I want to talk about is points of conflict and synergy between lattice cryptography and quantum computing. So as I guess everybody who's attending knows, Simons is actually running two programs right now, one on lattices in computer science and one on quantum computing. And I think it's a great idea to have these two programs together because there's many points of intersection. And what I want to do in this talk is to give a very, very high level and sometimes oversimplified, but I hope still insightful overview on some of these points of intersection and interesting directions in sort of putting together lattice cryptography and quantum computing. All right, so let's start with quantum computing. You have to start with one of them. So a quantum computer is a device that uses the physical principles of quantum mechanics in order to achieve new computational capabilities. And we have an illustration of a qubit here, the basic unit of information for quantum computing. And why are quantum computers good? A very interesting application is just to be able to simulate quantum physical processes. So we have some quantum physical systems, and we want to know how it behaves, maybe under different conditions, different temperature, different pressures, I don't know. So one way to do it is to just run the experiment, but maybe we don't want to actually make the setup to run the experiment every time, and we want to be able to simulate it on the computer. And since it's a quantum physical system, we actually need quantum computational capabilities for this purpose. And this is useful for scientific purposes, but also for industrial purposes like perhaps designing new drugs and materials and so forth, probably some that I don't even know about. Another application of quantum computers is to generate randomness. So using a quantum device, you can actually generate true randomness that is guaranteed to be uncorrelated with any other randomness in the world, which is a good idea, for example, if you use this randomness as a key for your cryptographic scheme. And this is opposed to what we sometimes do now, which is to use stochastic randomness, which comes, let's say, from the least significant bit of the clock of your computer or things like that. Another application which is of particular interest for this talk is to use quantum computer to solve cryptographic problems, such as factoring or discrete log problems. So in cryptography, we base the hardness of cryptographic schemes, the unbreakability, the security of cryptographic schemes on the hardness of computational problems. And indeed, many of the cryptographic schemes that we use today are based on the hardness of factoring large numbers or computing the discrete log over some groups. And using a quantum computer, these problems can actually be solved efficiently in polynomial time, which is a problem for the cryptographic use of these schemes. So quantum computers are great. And the first thing that we want to do is to actually build them so that we can unlock all these great applications. And the second thing that we want to do is to protect against them. And this is not necessarily in this order, since, as we said, if once quantum computers are built, they're going to render some of our cryptographic schemes insecure. We should already prepare with new cryptographic methods that will allow us to have secure cryptography even in the presence of quantum computers. And lattices are one of the most promising, or maybe the most promising approach towards obtaining quantum secure, post-quantum secure cryptography. And in the sense that it allows us to construct cryptography that, as far as we know, is resilient to quantum attacks. But before we sort of put all our eggs in this basket, we need to really sort of try to understand as much as we can what makes these lattice problems presumably resilient to quantum attacks, and maybe in terms of scientific curiosity, even if we don't completely break lattice cryptographic schemes, we want to understand whether quantum algorithms can, in any situation, outperform classical ones in the lattice setting. So at this point, I think I said the word lattice like maybe 10 times, but I should actually tell you what lattices are, and we're going to do this right away. So a lattice is essentially a periodic discrete set of points in Euclidean space, usually a high-dimensional Euclidean space. On the slide, of course, I only have two-dimensional Euclidean space. So you have an example of a lattice. And indeed, it looks like this infinite grid of points. I can now draw an infinite grid of points. So I drew a finite section of a lattice. And the property is that if you take two of these lattice points and add them together, then you also get a lattice point. You can also think about it as a discrete additive subgroup of the Euclidean space Rn. And usually the dimension grows asymptotically. And if you want actual numbers to keep in mind, then just think about, like, say, 1,000-dimensional lattice. So it's big. It's much bigger than 2. And the way that we represent the way that we represent a lattice is using a basis. So if I want to sort of give you a handle on the lattice, give you a representation of a lattice, then what I can give you is a set of vectors such that all the lattice points are obtained as integer combination of these vectors. And in this case, the dimension of the basis is 2 because the dimension of the lattice is also 2. So the basis actually spans the lattice when you have integer coefficients for the basis vectors. A basis is a representation of the lattice, but it's not a unique representation. So a lattice can have many different bases. So for example, this is also a basis for the same lattice, I hope at least. So a lattice can have many bases, and they can have very different properties. What are the computational problems that we care about when we talk about lattices? So the most basic problems that are usually considered are the shortest vector problem and closest vector problem. So in the shortest vector problem, you're given a basis for the lattice, and you're asked to find the shortest non-zero vector element in the lattice. So it's kind of easy. It's this guy, or this one actually. So the reason why it's easy is because what I gave you is a two-dimensional lattice. As the dimension increases, the hardness of the problem seems to scale exponentially actually with the dimension of the lattice. And this is actually becoming a hard problem. And we even care about the approximation version of this problem. So you don't have to even give me the shortest vector in the lattice, but some short vector that is not much longer than the shortest one. You can also think about the closest vector problem, which is I'm giving you a target point, like any point in space, and you need to give me back the lattice point that is closest to this target point, or some point that is not too far from this target point. So these are sort of two canonical problems for lattices, but actually when we work with lattice-based cryptography, we usually base this on a variant of this problem known as bound distance decoding. And this can be seen as sort of an extreme version of the closest vector problem, where we want to we get a target point and we want to find the closest lattice point, but we're guaranteed that the closest lattice point is actually very, very close. So there's a lattice point that is closer to our target than any other, is much, much closer to our target than any other lattice point. And even under this promise, we want to be able to find the closest lattice point. So by the way, these problems, sometimes it's instructive to think about them as Euclidean analog of decoding problems. So if you think about error correcting codes, then again, you have these type of problems where you're getting a word that is guaranteed to be close to a code word. So it's taking a code word plus a little bit of noise, and you want to be able to decode and get the code word that you came from. So let's talk about the bound distance decoding BDD a little bit more. Be slightly more formal, although I'm not going to be very formal in this talk at all. So one way to generate an instance to BDD is the following. So I'm going to take the 0 point and perturb it a little bit, and I'm going to get what I want to think about as the noise value. So it's this value E, which is very small. This value E actually defines a coset for this lattice. So there's this set of green points, which is just a coset of the lattice of blue points. And in the bound distance decoding problem, I'm given a random element in this coset, or I can also think of the canonical representation of this coset. And the goal of the solver is given this input to actually find E, which is equivalent to finding the closest lattice point to this point Y on the slide. And this has a very simple linear algebraic representation. I can think about the point Y as taking the basis represented as a matrix times a vector S, which is an integer vector, plus this small perturbation. So I'm giving you this sort of very simple linear equation with S and E that are hidden. And the goal is to sort of recover the value. The notion of approximation here, so the approximate version of BDD actually sort of refers to how close the point y is to a lattice point compared to the second closest lattice point, let's say to y, or the distance, or the minimum distance between two lattice points. So how extreme we get in sort of enforcing this promise that the target point is close to the lattice. So these lattice problems, in particular BDD, are really a cryptographic treasure for a few reasons. One is that they lead to like a fantasy land of crypto primitives, and I'm not going to get into details. I'm just going to refer you to the workshop that's going to take place at Simon's next week about cryptographic applications of lattice problems. Really some applications that we maybe a few years back would have been considered sort of speculation, we can actually found on the hardness of lattice problems. The other useful property is that lattice problems enjoy worst case to average case reductions, which means that there exists a distribution of BDD instances, so of lattices and points, such that if you sample an instance from this distribution, then you're guaranteed that it's at least as hard as solving BDD or even other lattice problems on worst case lattices, so on any lattice in the world. And this is very useful for cryptography because we don't need to think very hard on which distribution to use for our crypto system. So for cryptography, we need to sample an instance. And this gives us a way to sample an instance that is, in a sense, the hardest one. So this is also a useful property. And the last property is, well, the resilience to quantum attacks, which is what we're going to talk about now. So let's try to see how quantum attacks actually solve legacy cryptographic problems, and then try to understand whether we can do something also for the case of lattices. So the way quantum algorithms, and again, this is going to be very high level, the way quantum algorithms solve problems like factoring or discrete log is by casting them as problems known as period finding, or hidden subgroup problem. And I'm going to talk about period finding, this is the following problem. So the task that we have is to find a hidden number p. You can think about it as prime, but it doesn't have to be, given access to an oracle that depends on p. Of course, it really depends on what this oracle is. We're going to talk about it in a second. But the running time should be polynomial in the size of the representation of p. So the running time should be polylog in this number p that we have. So what is this oracle O of p? So let's start with an easy oracle. So let's think about an oracle that, given any integer x, just returns x mod p. And of course, finding p given such an oracle is very easy, even classically. So note this oracle actually always gives you the same answer on every coset of the integers modulo p. So the answer of the oracle only depends on the coset modulo p where your input is. But this oracle also gives you a very convenient name for the cosets. And the question is, what happens if the coset have random names? So let's just use colors. So instead of telling you what x mod p is, you're just going to input an x and you're going to get a response, I don't know, pink. And if you have two different x's that have the same value modulo p, then you're going to get the same color, but otherwise you're going to get different colors. And the question is, given an oracle of this form, can you find p? And now this is a harder task. And indeed, classically, you actually cannot do it in polynomial time, in polylog p time. But turns out that this is where quantum algorithms actually have an advantage. And the way that quantum algorithms actually solve this problem in polynomial time is using a technique known as quantum Fourier transform. I'm not going to define Fourier transform. I assume that the vast majority of the audience know what it is. But anyway, all that we need to know for the purpose of this talk is that the Fourier transform is an operator on functions that have the following property, actually just one. So what I want is that when I feed the Fourier transform with a periodic function, so in this case, a function, by the way, you can see my arrow, right? Can you see my arrow that's wiggling here?
Yes.
Excellent. So when I'm giving you as input a periodic function, so in this case, this is a function with period p, then when you apply Fourier transform on this function, then the output is actually going to be a discrete function. And this function is only going to be supported over multiples of 1 over p. So periodicity in the input actually leads to discreteness on the output. And why is this useful? because given access to this color oracle that I described, we practice hygiene here. Given access to this color oracle that I just described, we can actually generate a quantum state which is in superposition over sort of over a given coset mod P. So given a sort of a monochromatic, set of points. So I didn't say what quantum state is, and I didn't say what a superposition is, but for our purposes, it suffices to say that a superposition or a quantum state can represent a function, of this form. And using the color oracle, I can generate a superposition which is periodic over the cosets of the integers mod P. So once I generate the superposition, I can apply this quantum Fourier transform, which can be done efficiently. This allows us to perform the Fourier transform operation on the function that is defined by the quantum state. And this is going to give us a new quantum state that is only supported over multiples of 1 over P. Then what we do is measure this quantum state, which is again something that I didn't define, but for our purposes, when you measure a quantum state, you get some value in the support of this state with a probability that is proportional to the square of the amplitude. But again, these details are not going to matter for us. What's important is you're going to get a multiple of 1 over P. And if you do this like a couple of times and you get a few multiples of 1 over P, then you should be able to recover 1 over P and then recover P itself. And this is how these algorithms work. And of course, I'm omitting a lot of details. So for example, a periodic function is necessarily infinite, whereas the quantum states that we can efficiently represent are necessarily finite. So we have to take that into account. But all of these things can be resolved. I think the high-level picture that I want you to have is that we start from a periodic function over the cosets and go to a discrete function over multiples of 1 over P. And this is the tool, and you can actually use that to solve factoring and discrete log. Actually, this also works in higher dimensions, and sometimes you actually need it for some of these problems. And interestingly, you can even think about it in lattice terminology. So we can think about the lattice, this is a one-dimensional lattice of all multiples of P. And if we think about this lattice, then this function we can actually think of as a periodic function over the cosets of the lattice. So it's a function that is defined over the entire space, but for all the points that belong to the same coset of the lattice, this function takes the same value. And what happens with quantum Fourier transform when you apply, or with Fourier transform, when you apply Fourier transform on such a function, on such a lattice periodic function, what you actually get is another function which is discrete and is only supported over a different lattice. Now the lattice is the multiples of 1 over P. And this different lattice is known as the dual lattice of our original lattice. And a nice way to think about it, even though again, this is not fully rigorous, but it can be made rigorous, is that the dual lattice is essentially the Fourier transform of the original lattice. In the sense that if you're periodic over the original lattice, when you apply Fourier transform, you're going to get something that is discrete over the dual lattice. This is how we solve factoring and discrete log. And now let's see if we can sort of take these techniques and port them to the lattice world. So, you know, the least that we need to check is that we can just sort of apply it and just get the polynomial time lattice algorithm. That would be unfortunate for lattice cryptography, but a good thing for quantum algorithms. So again, as I said, this sort of period finding or quantum Fourier transform technique actually allows you to recover a basis for the dual lattice. So all these multiples of 1 over P that we recovered, if you think about in the high dimensional regime, it is actually going to give you a bunch of points in the dual lattice, which you can sort of put together to actually get a basis for the dual lattice. So this is something that you can do, but these are not the problems that we talked about before when we talked about hard lattice problems. So this is not going to allow you to find short vectors in the lattice or to do decoding. And the reason is that if you're only thinking about sort of using some sort of color oracle or only using the fact that a function is fixed on all the points in a coset, we actually don't take into account the geometric properties that actually define the problems that we want to solve. So we want to be able to decode for cosets that are very close to the lattice point. But like the color oracle that I described before doesn't even distinguish between cosets that are close to the lattice and cosets that are far from the lattice. So this sort of technique, at least as is, seems to lack a sort of very strong component that will allow it to be applicable for the lattice problems that we care about. But let's not give up just yet, because it seems like this technique is powerful and does give us something also in the context of lattices. So let's sort of not give up just yet and try to see what we need to do in order to be able to adapt this technique also to the lattice regime. So the things to keep in mind is, as I said, we need to use the geometry. We need to take the closeness into account. The other precaution that we need to take is to sort of not to do too well. And the reason is that the exact version of these lattice problems that I mentioned are NP hard, and we also have a worst case to average case reduction here. So if you come up with a quantum algorithm, then it has to somehow discriminate between instances between the parameter regimes of the problem that are NP hard, which we don't usually hope to solve in BQP in quantum polynomial time, and these instances on which we wish to get an advantage. So if you want to get an algorithm that has advantage on the lattice problem, then it needs to take this point into account. And what I want to talk about next is a few cases where we actually can get some advantage using in the lattice regime using quantum techniques. So this is not going to be a quantum polynomial time algorithm for general lattice problem. This is not something that we know how to get. But it is going to be cases where we have quantum techniques that allow us to perform some computational tasks that we don't know how to perform classically in the context of lattices. So I'm going to mention 3 examples. One is in the context of quantum reductions. So we don't know how to actually get quantum polynomial time algorithm for lattice problems, but it is possible to show that if you have an appropriate oracle, then you can actually take advantage of this oracle in quantum ways that you cannot do classically. And I'm going to say more about this in the next slide. And this actually leads to quantum reduction. So it's reductions between problems that we can perform quantumly, and we don't know how to do classically. The second example that I'm not sure that I'm going to get to talk about in detail is, again, you can think about it as a type of reduction, and this is a way to use non-trivial quantum algorithms for a problem known as the Dihedral Corset problem. So this is a problem that is defined on a quantum input, and for which there exists a non-trivial quantum algorithm. And it's possible to show that this problem is actually connected to lattice problems. And in fact, if we can get slightly less trivial, even less trivial algorithms than the one that are currently known, then this will actually lead to quantum advantage for lattice problems, even in the general setting. I should mention that whenever I'm talking about sort of quantum speed up or quantum advantage and so forth, in the context of this talk, I'm talking about superpolynomial speed up. However, in many settings, you might care about polynomial speed up as well. So I thought I'd mention it. So polynomial speed up could also be important for quantum cryptography. But in this talk, what we care about is superpolynomial speed up. The third example is actually the first thing that I'm going to very briefly mention. And this is actually a case where we do have superpolynomial quantum advantage for lattice problems, but not for general lattice problems, but for a specific class of lattices that are known as ideal lattices. So let me very briefly not tell you what ideal lattices are, and yet try to sort of give you an idea on what happens here, because I think it's really nice. And you'll see in a minute why I'm calling it cheating. Of course, the algorithm works, it's not cheating. But it's cheating in the sense that it doesn't follow these guidelines or warning signs that I just mentioned. So it's very nice that you're able to get around them in certain cases. So in this case, there's a quantum polynomial time algorithm that solves BDD and also other lattice problems on this class of ideal lattices. And it does so, and it gives an approximation factor that if you wanted to get classically, you'd have to run in sub-exponential time. So it's a significant advantage. And the one thing that I'm going to tell you about ideal lattices is that this is a type of lattices that can be represented by a generator, which is an algebraic object. And this generator actually defines a basis for the lattice, but an ideal lattice also has bases that are not necessarily a generator. This quantum advantage here is achieved by an algorithm that takes 2 steps. The first step is to find some lattice generator. Not all bases for the lattice are generators, so we need to work in order to be able to find some generator for the lattice. And here I don't care about the geometry of the lattice. All I care about is this sort of algebraic task of finding a generator. And the second step is going from this generator, which could represent a long basis for the lattice, so a bad basis for the lattice, to a generator that represents a short basis for the lattice, which allows us to solve the BDD problem. And the nice thing here is that you use the quantum techniques only for the first step. So the first step, which actually doesn't care about the geometry, is the one where we use the one where we get the quantum speed up. And then for the second step, you do use the geometry. You have to use it somewhere, but you only use it in the second step to go from the long to the short generator. So this is sort of a way to sort of get around what I said before, that your quantum algorithm needs to take the geometry into account. In this case, you take the geometry into account in the classical part of the algorithm. So this is really cool, and this is a really interesting and exciting avenue for research, whether you can extend it into other regimes and other classes of lattices. I should mention that as it stands, it's not applicable for standard cryptographic regimes, both because of the approximation factor that is being achieved, which is usually bigger than what people use in crypto, and because ideal lattices are usually not used for cryptography per se, used related lattices that are known as module lattices, and for that kind of lattices, we don't know how to get this kind of speed. So now let me spend some time talking about this SIVP to BDD reduction this is a reduction by Regev. I did not say, and I will not say what this SIVP thing is, but let me sort of say what we're actually going to show. So what we show is that if I give you access to a BDD oracle, so an oracle that solved this BDD problem that I described, then it's possible to find short vectors in the dual lattice. So remember this dual lattice that we talked about. I didn't show you what the dual of this lattice looks like, but we're going to be able to get vectors in the dual lattice that are fairly short. And why is this good? Well, for once, if you have short vectors in the dual lattice, then you can actually solve the BDD problem. So this gives you a way to start from a BDD oracle, and just by sort of having oracle access to this to the solver of this problem, you can actually sort of recover what's known as a trapdoor, or as a way to actually solve BDD for any instance in the future without actually looking at this oracle. So this is sort of a very nice property to have. And let me sort of more specifically say that when I'm talking about a BDD oracle, this is an oracle that takes as input a lattice basis B and a vector Y, and recovers this perturbation E that we were talking about before. I should say that this reduction is also sort of lattice preserving. So I'm giving you a BDD oracle for a given lattice, and you're going to get short vectors in the dual of this specific lattice. So this is also sort of a nice feature here. You don't need to solve BDD on all lattices in the world.
So can I ask questions, Zvika?
Yeah.
So when you said that eventually you can solve BDD, that's in the original lattice, right? Not in the.
That's in the original lattice. Yeah. So if you have short vectors in the dual, this allows you to solve BDD in the primal lattice, in the original lattice.
Hi, Zvika. Do you need the BDD oracle to work with probability 1, or it works with any small probability?
So it's suffices that it works with small probability, but for the purpose of this slide, I'm going to assume that it works with probability 1.
Okay.
Okay. So good. So the first thing that we notice when we try to do something with a BDD oracle is that it seems kind of useless when you try to play with it, because in order to use a BDD oracle, I need to feed it with a lattice. I need to give it a basis for the lattice B, and also the point Y, which needs to be close to the lattice. How do I generate this? How do I generate this point Y? So if the point Y is not close to the lattice, then the oracle can do whatever it wants, and maybe I'm not going to be able to get any useful information out of it. The obvious way to do it is to take a lattice point and perturb it a little bit. And indeed, this way you will get a point Y that is a valid input to the oracle. But in that case, the response of the oracle is completely useless, because it's only going to give you back the perturbation that you started from. So at least at first glance, it seems like it's going to be pretty hard to take advantage of a BDD oracle. But let's not lose hope. Let's sort of go back to our quantum Fourier or the Fourier transform tools and see how this Fourier transform, which again relates periodic functions on the primal to discrete functions in the dual, can help us in sampling short vectors in the dual. And indeed, the point is that the shape of the periodic function is going to matter. So before, when I talked about the color oracle, I was talking about uniform superposition over a coset. Now what we're going to do is generate a superposition with an appropriate shape, such that when you take the quantum Fourier transform, when you take the Fourier transform of this shape, you are actually going to be supported only over or mostly over short vectors in the dual lattice. And yeah, so this is going to be our goal, to generate a quantum state whose quantum Fourier transform is mostly supported over short points in the dual and not over uniform points in the dual. And I'm not going to tell you why this is the case. Those of you who worked a little bit with Fourier transform probably sort of at least have some intuition. But if I could replace each lattice point with just a ball, and I define a function, again, this lattice periodic function that is defined by the sequence of these balls, then the quantum Fourier transform of this function is indeed going to be supported mostly over short vectors in the dual. So this is going to be our task now, to generate this superposition. And if we can do this, then we're going to be able to sort of solve our problem and get short dual vectors. And these balls should have a radius as big as we can get, but we'll see that we're going to have a limitation on the radius of the balls that we can generate. Good. So let's see how do we generate this type of superpositions? How do we generate this type of superposition? So the approach is actually pretty similar to what we tried to do before when we sort of attempted to classically utilize the BDD oracle. So we can generate a superposition over all the lattice points. And then for each of these lattice points, actually create a little ball around it. This is something that you can actually do efficiently, but it suffers, even though it's quantum and it's a superposition, it suffers from the exact same problem that I mentioned before. Each point in the ball that you generate is actually sort of remembers or is associated with the lattice point that it came from. And this type of superposition is actually very different from a superposition of balls that sort of don't remember the lattice point that they originated from. So the task now is to start from the superposition of sort of centered balls and remove the center of the ball. And this is what we're going to use the BDD oracle for. So notice that if we sort of feed any point in the support of this, any point in the support of the superposition into the BDD oracle, it's going to give me the center of the ball that I started from. And this is guaranteed that the balls are small enough that the BDD oracle is actually supposed to be, is guaranteed to solve on this radius. So the BDD oracle actually allows us to compute, given any point in the superposition, the center of the ball that it came from. And in the quantum regime, if you can compute something, then you can also erase it. So being able to compute the center of the ball actually allows you to remove the centers from all these balls and arrive from this centered superposition into this sort of just superposition of balls without origin that is required in order to get this sampler for short lattice points. So this is, yeah, I see that there's a question.
Sorry, I'm not sure if I understand what it means to remove the center. In terms of your picture, it looks like, you know, I can always see the center anyway.
It's not clear that you can always see the center anyway, right? Because if you look at this, if you look at the superposition, so if you're just thinking about, so the superposition, you can think about it as like just a formal sum of all the possible points in this regime. So you're actually going to have a formal sum of all the points in all the balls. So if you're looking at a given point in the sum, then you're not necessarily going to know what is the center of the ball that this point belongs to, because this is exactly the BDD problem. You cannot do this efficiently. So it actually does have a meaning whether you, whether I'm telling you, whether it's a formal sum over like a point and the center that it originated from, or whether it's a formal sum only over points without center.
So just to make sure
this actually makes a difference.
Let me just make sure I understand this correctly. The center is still information theoretically determined. So when you remove, it's sort of in some sort of a computational or representation.
Right. So yeah, information theoretically, I can always generate these things. Information theoretically, there's no problem. The question is how to do it efficiently. And in order to do it efficiently, I need something like BDD. I need to be able to sort of get from a point in the ball onto its respective center. So yeah, there's another question.
Yeah, still about the same. So the distribution that you generated is always correct. Can I think of it as that before you remove the center, there's some sort of register that has the center written in it? After you remove it, then that register disappears.
Right. Yeah, I didn't want to get into sort of formal description of quantum registers and so on, but since you asked, let me say it. If you don't want to know about quantum registers, you can wait until I'm done with the sentence. So yeah, so what you get is you have two quantum registers, one that contains the center, and this is going to be a superposition over all lattice points, and the other one is going to contain these the elements of the balls. So the element in the ball is always going to be associated with its center. And what we do using the BDD oracle is sort of erase the information in the register that contains the center, so that we can sort of remove this without collapsing our superposition and actually get the balls that we need.
Thanks.
Good. Yeah, so this is what I want to say for now about sort of quantum algorithms for lattice problems. And let me talk a little bit about the synergy part. So about how to use lattice cryptography in order to improve the way that we use quantum computers. So remember when we talked about quantum computers, and we said that, was there a question?
Yes, this is Vinod.
Yes.
So this type of reduction, we don't know how to do it without quantum, right? But we don't have any negative indications, right? There's no negative results,
right,
that say, you know.
Yeah, you're preempting my open question slide. Yeah, but there's certainly a good question whether this type of reduction, or any other reduction between BDD and SIVP can be done without quantum powers. Right now we don't know how to do it, and not for lack of trying, I think. But there have been many cases where we had quantum advantage, and it turned out after a while that there's actually classical methods to achieve similar performance. So there are other tricks that you can do with the BDD oracle that give you non-trivial advantage for other problems, but not for this problem of finding short vectors in the dual lattice. So I think there was another question.
Maybe, yeah, me. So as you were talking about reductions, this is Daniele.
I can hardly hear you, so if you can speak a bit louder.
So is it better now?
Yes.
Okay, so as we are talking about reductions, so you refer to this BDD as an oracle, but it's not entirely clear if an oracle is really enough. I mean, if I give you an oracle that is implemented, you don't know how, but perhaps it is, exponential time or anything. I tell you, oh, you can make queries. I'll give you the answer. Maybe you can even make quantum queries. I will give you the quantum answers. But is this enough to carry out the process that you are describing? Or you do need indeed a circuit, and you need to say that, oh, this operation can be performed by a polynomial size circuit?
Right. So if I understand correctly, you're talking about what your question applies even to what is the notion of a quantum reduction, right? So normally when we talk about reductions, what is the purpose of showing a reduction between problems? Sorry for starting with sort of a very sort of trivial statement. So when we show reduction, right, what we want to say is that if we have an efficient algorithm that solves problem A, then we're going to have an efficient algorithm that solves problem B. And it is indeed a question of how to state this also in the quantum setting. So certainly you need to define what it means to actually get quantum access to an oracle. And this notion of reduction needs to sort of respect we respect our goal, which is to say that if we have an efficient quantum or classical efficient quantum or classical algorithm for problem A, then we also get from the reduction an efficient algorithm for problem B. Is this your
impact? But so let me more directly ask: would you say that this reduction is black box or non-black box?
So I would say that the reduction is black box, but it is true, and it is interesting to think what is the correct notion of a black box reduction in the context of quantum algorithms. So, for example, if you given oracle access to a quantum algorithm is actually weaker than being given the circuit, even in ways that we consider to be black box. So, for example, if a quantum algorithm is represented as a circuit, then if I'm giving you the actual circuit, then you actually have a way to recover a circuit that computes the inverse of this function. So if I'm giving you oracle access to a function in the quantum setting, if I'm giving you sort of black box access to a function in the quantum setting, then shouldn't I also give you an oracle not just to the function itself, but also to some inverse of this function, or to a way to do conditional execution of this function? So the question of what the difference between oracle access and black box access in the quantum setting does make sense, but here we're actually using the weakest notion, which is all I'm asking is to have quantum access to this oracle.
Okay, thanks.
Okay. So yeah, so we said that quantum computers are great, and we should try to build them. So going back to point number one, let's try to build a quantum computer. So this is a hard task. You don't just need one qubit, you need many qubits, and you need to connect them in the right way, and you need to keep them coherent, so keep them from losing information to the environment. And these are sort of engineeringly hard tasks. And scalable, so fully scalable quantum computers that can run any quantum algorithm that we want seem rather distant as things stand. And I should be careful in this audience. So if someone in the audience has something to report in this respect, then I'll be happy to hear some news about this. But as far as I know, it seems like we're still pretty far from fully scalable quantum computers. So this means that we should not expect them in our living room anytime soon. And when they are built, it's more likely that they're, at least the first step, they're going to be owned by, say, big companies, and we're not going to have direct access to them, but rather only access from remote. And this brings up the question of how to utilize a remote quantum computer that is possibly owned by an entity that you don't necessarily trust. So the setting that we're going to have as in the first step, probably of quantum computing, is that they're going to be some entity that claims that they have a quantum computer. And we, with our classical calculator capabilities, are only going to have classical communication access to this supposed alleged quantum device, and we still want to get utility out of this situation. So this brings about a bunch of questions, and it turns out that lattice cryptography can actually be helpful in sort of approaching a number of these aspects that come up in this setting. So the first thing that I'm going to mention is this notion of proof of computational quantumness. So someone claims that they constructed a quantum computer, and the first thing that you want to check is that indeed this device can perform a computational task that we don't know how to perform using a classical computer. So this is actually indeed done using techniques that are not lattice cryptography, but as I'll try to explain in the next slide. If we use lattice crypto, then we can get proofs of quantumness with sort of favorable, some favorable properties to what is currently known. So next thing, maybe you don't just want to show that your device can do something. You actually want to use it for like a useful purpose. And one thing that you can hope for is to use the quantum device to generate randomness for you. But you want to generate it in such a way that you're certified that the quantum device indeed sort of used quantum measurements in order to generate your randomness. And it's not just sort of giving you classical randomness and claiming that it's quantumly generated. So this is this notion of certifiable quantum randomness. Another task that you can think of is verifiable delegation. So you have a quantum algorithm, and you're giving the algorithm to the untrusted quantum device in hope that it runs it. And you want to verify that indeed this quantum device executed the algorithm that you wanted. So you want to get some proof or ability to verify classically the outcome of a quantum computation. Another thing that you want to do with a remote server. So I'm going with sort of increasing levels of sort of optimism. And once everything is solved and we know that the quantum this quantum device actually does what we want it to do, well, we can also try to think about privacy. And when we send information to this quantum server to compute on, maybe we want to maintain the privacy of our input. And this leads to this notion of private delegation or quantum fully homomorphic encryption, which is somewhat related, but also quite different from this notion of blind quantum computing, for those of you who know what that is. So we want a way to sort of completely classically encrypt information and still allow a quantum device to process it. And it turns out that you can use lattice-based cryptography in sort of the obvious sense that we use cryptography, right? Cryptography gives a weak entity the ability to sort of, it gives the weak entity sort of leverage even over some stronger adversary. And if you have quantum resilient cryptography, then you get leverage even over quantum adversaries. So Thomas Widig has this sort of calls it the classical leash. Having cryptographic leash on quantum computers, and I think it's sort of a nice picture to keep in mind. So the cryptography actually allows you to sort of put a leash, even if you're a classical entity, on a quantum device. So the last thing that I want to talk about a little bit more is about this notion of proof of computational quantumness. And sort of the different approaches and what is the difference of the approach that uses lattices. So as I said, in this context, what we want is to demonstrate a computational task that can be performed by existing quantum computer, but not by a comparable Turing machine, or by comparable classical device. And I should say that, at least in my opinion, this notion of proof of computational quantumness is somewhat of a philosophical question more than a mathematical question. We're not going to have like a proof or even a practical question. We're not necessarily going to have a proof that we achieved computational quantumness. All we have is evidence sort of saying that a certain computational task we do not expect to be performed by a comparable classical computer. So what it means for a classical computer to be comparable to the quantum device that we're talking about is also something that is not formally defined and is subject to interpretation. And of course, what we really want is to sort of demonstrate this asymptotically, but this we can never do. The only thing that we can hope is to sort of demonstrate it on sufficiently large inputs, so we're convinced that this actually something asymptotic is happening. But still, we really want to achieve this task. For once, because there's a lot of money and a lot of energy going into building these quantum computers, and we want to know that at least we're doing something that was not achievable before using classical devices. And the second thing, sort of maybe more scientifically or philosophically, is that this is going to give evidence for refuting the extended Turing hypothesis that says essentially the opposite, that any sort of process occurring in nature, you can simulate using a classical device with comparable resources to this sort of physical process that you started from. If we show, in particular, quantum computation is a physical process, and if it cannot be performed by a classical device, then this is evidence for refuting this extended Turing hypothesis. So how can we do this? How can we do proof of quantumness? So one thing is to just use Shor's algorithm. As I said, we have a quantum polynomial time algorithm for these problems that we don't believe to have a classical, or that some people believe that there's no classical algorithm for, or currently not known at least. So under the complexity assumption that the factoring or discrete log problem is not in BPP, is not computable in polynomial time, if we can implement Shor's algorithm, then we can get proof of computational quantumness. The problem here, of course, is, as I said, that actually running this algorithm requires a scalable quantum computer, which is currently out of reach technologically. The other approach, which actually works, is sort of more tailored to the quantum devices that are currently already constructed. And the idea here is to use the existing quantum device in order to sample from a distribution which is hard to sample from using classical device. So again, this is under a complexity assumption that there exists a distribution, this particular distribution that these quantum devices sample from, and this distribution cannot be sampled from using just classical randomized algorithms. So again, you need to sort of assume some separation between what can be done in quantum polynomial time and what can be done in sort of classical randomized polynomial time. And this approach indeed works and is implemented, and Google has run this experiment. They call this notion quantum supremacy, and they were able to sample from this distribution, which is assumed to be hard for classical samplers. But now that they have this collection of samples, the question is, how do you verify that the quantum device actually samples from the correct distribution, even if you do accept the assumption that this distribution is hard for classical devices? And the way that this is currently done is by sort of employing very strong classical supercomputers that run in exponential time and verify the result of this computation. And this brings up a lot of challenges and a lot of questions, but in particular, the problem is that this approach seems to only take us to like the current level of technology. Once quantum computers become large enough and we want to sample from distributions that are complex enough, so we want to know that we actually have quantum capabilities of 100 qubits and not of 50 qubits, then running in classical exponential time to verify is actually going to become completely unfeasible. So this approach works very well and achieved this great result with respect to current technology, but there are questions of how you can scale it as quantum computers become more and more elaborate. The third approach that I mentioned before, relying on lattice cryptography, is actually by doing a multi-round protocol. So both the approaches that I mentioned so far are just doing challenge response. You send something to the quantum device, and it sends you something back. Here we actually have something that runs in, actually our basic algorithm, the basic protocol runs in just 4 rounds, but still it's not just challenge response. And the assumption that we use is the hardness of lattice problems. And this is a little interesting because lattice problems, as I sort of just said so far, are assumed, or as far as we know, are hard even for quantum devices. So assuming that the LWE, or assuming that lattice problems are hard, actually does not separate the complexity class BQP from BPP. And yet, even though we're relying on an assumption that does not separate these complexity classes, you're still able to show a quantum computational task that is presumed to be hard classically. So this is one sort of interesting feature of this approach, at least theoretically. In terms of practice, or in terms of efficiency, at least, our verifier does not need to run in exponential time. It needs to run in polynomial time. However, the verification process is not public. So since we're using cryptography, this classical verifier is actually going to sort of generate some secret key that is going to help it. Just a second. It's going to generate a secret key that it's going to use in order to sort of try to catch the quantum device. So we get efficient verification, but this efficient verification requires a secret key. What was the question?
Zvika, I think I missed what you said about assuming LW is hard. It doesn't imply something. It seems like there's an analog between 1 and 3, which is that if we believe LW is hard, then the same way we believe that factoring is hard, then.
So notice that here we need to assume some separation between BQP and BPP. We need to assume that there's a computational problem that is solvable in quantum polynomial time, but not in classical polynomial time. Here we don't make any assumption. It's possible that BQP is equal to BPP. So any language that is decidable, or even any distribution that is sampleable using a quantum device can also be efficiently sampleable by a classical or computed by a classical computer. And yet you can sort of devise an interactive computational task that sort of separates these two things. So you can have quantum advantage even if BPP is equal to BQP, which is kind of nice to think about. So this leads me to the end of the talk, sort of looking ahead. Some of these things you already asked. So it's very important to sort of continue and try to explore further and understand where and what type of quantum advantage we can get for lattice problems, in particular in the cryptographic regime. And this is important also for the real world because people actually intend to use lattice cryptography. And people do intend to construct quantum computers. So these things are going to sort of meet, hopefully, at some point in the future. So the example that I gave with ideal lattices is something that I think is not fully understood to what is the extent that you can bring it. Is there actually a gap between ideal lattices and general lattices in this context, and how much more you can leverage this type of techniques? Dequantumizing the reduction that we talked about is a question that already came up. Another point that I did not mention so far is to try to sort of apply these quantum techniques also to other allegedly quantum resilient cryptographic problems, such as problems that rely on error correcting code. So decoding problems that relate to decoding of random error correcting codes, such as the learning parity with noise problem. So if I said that in the quantum techniques, we only know very little, in the coding regime, we know, I want to say nothing, but I know nothing. I don't know of any way to sort of get analogs of the things that we know in the lattice regime to work in this coding regime, and that's sort of very interesting question. What it actually means for the quantum hardness of these problems. In terms of using lattice cryptography in the quantum setting, as I said, we want to be able to generate sort of this notion of scalable proofs of quantumness. So we want to actually be able to, this is even a question of definition, to define what it means that you didn't just prove to me that you have quantum powers, but you proved to me that you have 100 qubits worth of quantum power. And actually devise algorithms that don't only guarantee that you did something that could not have been done classically, but also something that could not have been done using a smaller quantum computer. So this is something that I think should be addressed. You can think about improvements for this certifiable randomness and verifiability protocols that I did not talk about, and better understanding of the power of this cryptographic leash. This is still a new technique, and we essentially have just one example of how to use it, given lattices, given lattice cryptography, and it's important to understand whether we can use it in other places or find other instantiations for this type of technique. Thank you very much. Yeah. I think we're probably out of time, but I'm happy to answer questions. Yeah.
Any question in the audience here? No.
I have a question.
Yeah.
Zvika, this is Shweta. Can you go back to your second last slide?
This one.
This one, yeah. So I'm just trying to understand this proof of computational quantumness. As I understood, you said that if I'm a weak device and I'm going to have to talk to a quantum computer that's owned by industry or something, right? I want to make sure that they actually have the quantum power that they're claiming to have. So this is a proof that gives us that, right? So we get convinced.
It proves that whatever it is that they're doing cannot have been done by a classical device.
Exactly. Yeah. So I got that. What I'm trying to understand is that in terms of the usual applications that we have, where there's a weak client and a powerful server, right? So this proof of computational quantumness has to be built in into every application that we have. What I mean to say is that, let's say that, you know, we run this proof of computational quantumness, and now I'm convinced that Google or whoever it is that I'm talking to is indeed a powerful quantum computer. How can I be sure that next time when I ask them to do some work for me, they're actually using this quantumness? So,
right. So yes.
Yeah. So yeah, that's the question. So basically, I want to not just know that they have this power, but I want to be sure that they're using it for me. So in some sense, just knowing that they have the power is not really going to help me, right?
Right. So this is a completely accurate, what you just said. So just knowing that they have the power is not going to help you. This is just the first step. However, if you invested a lot of money, time, effort, and energy in constructing a device, and you're saying, well, you know, it's going to take, I don't know, 5 more years, 10 more years for this device to do something useful, then at least as a sanity check, you'd want to know that that you're on the right track, right? So this is a way. This is by itself, this proof of computational quantumness is by itself not necessarily useful for any particular task, but rather just a way to show that we managed to construct a device that has powers that are different from the devices that were known to be constructed so far. It has a very limited capacity, and this is why I only mentioned it sort of as a first step in this sort of hierarchy of tasks that we want to perform once this sort of more and more elaborate quantum computers are actually constructed.
It's something then that's more useful from the server's point of view. Like if I'm the server, then I want to prove to you that I do have this power that classical computers don't have. It's not something we should think of as benefiting the client per se.
Right. The modeling is in the model of this client server, of this prover verifier, but actually, you know, in this setting, both of them are actually going to be the same entity, and it's just us that are sort of skeptical as to whether something that was constructed is actually a quantum computer or not. This is actually good also as a sanity check. Maybe, you know, I think that I constructed a quantum computer, but I want to verify, even for my own sake, that the thing that is constructed actually does the task that actually performs a task that is inherently quantum.
Yeah. But it is important for the verifier to be classical here, right?
Yes, exactly. Because you could think of a weak quantum device verifying a strong quantum device.
Yeah,
and this is something that has been studied in the literature extensively. But yeah, the ultimate goal is to be able to do it completely classically, so that even, you know, classical beings like you know, ourselves can be convinced without sort of any need for a mediator. We can be convinced that something quantum has happened.
Okay, cool. Thanks.
Anybody else? Okay, my guess is that the next talk we have will probably be all remote. I think it's kind of an educated guess. So I think that's next week in the workshop, right? Starting on Monday morning. I mean, that's the workshop talk. It was supposed to be in this room. So thank you very much, Zvika. I know it's
thanks everyone for tuning in, and thanks for having me remotely. Clapping to you.
Thank you, Zvika.
Bye.
Bye, everybody.
Bye.
Bye.